This is the last problem from lesson 1 that we skipped last time. It is on related rates. It says we've got two people, they're standing 50 feet apart, and then one of them starts walking north. It says that the angle increases at a constant rate of 0.01 radians per minute. So this person here is starting down here, and they're walking up this way. This person stays stationary. We are looking for the rate at which the distance between the two people is changing when theta is 0.5 radians. So we want the rate of change of this. So we're looking for dx dt. That's what we want to find. We need a relationship between the variables here. Notice as this person walks north, x is going to change. It's going to get bigger. Theta is going to change. It's getting bigger. But this distance right here stays constant. It is a constant 50 feet. So when you set up your equation, x has to be a variable. Theta has to be a variable. But this side can be a constant. So it looks like I have the adjacent side and the hypotenuse. So the equation I'm going to set up is cosine theta equals adjacent over hypotenuse. And then we need to take the derivative. The derivative of cosine theta is negative sine theta times the derivative of theta. Uh, 50 over x, I'm going to write that as 50x to the negative first. So the derivative is negative 50x to the negative second times the derivative of x, which is dx dt. We're looking for dx dt. We are given theta, so negative sine of 0.5. d theta dt is 0.01. We're not given x. X is not given here, but we can use this relationship up here to find x. So cosine theta equals x over 50. Or I'm sorry, 50 over x. If I multiply both sides by x, I would get here. So x is equal to 50 divided by cosine theta. So 50 divided by cosine theta, and theta is 0.5. So my x value is this 56.975. 56.975 times dx dt, and then we should be able to solve for dx dt. So we want negative 50 divided by that squared. And then, so that's this, and then I need to divide both sides by that. So negative sine 0.5 times 0.01, and then divided by that answer that I just got. So it looks like dx dt is 0.311. 0.311. Units are feet and minutes. Which is not very fast. The person's walking very slowly. Getting into today's lesson. We're looking at chapter 3. Chapter 3 is mostly on finding extrema and finding points of inflection. So looking at when the derivative is positive, the function's going up. When the derivative's negative, it's going down. Second derivative tells us about concavity. If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down, and could look at it like any of that. So example 1 is kind of just a review of how to find extrema as well as points of inflection. It gives us this f of x. Extrema always occur when the first derivative is equal to 0. So we want to take our first derivative, set it equal to 0, and solve. And we get x equals 3 or x equals -1. And then you have options. You can either use the first derivative test, which is where we set up our intervals, and check to see if it changes from positive to negative, which would be a max. Derivative is positive, and then negative, so that would be a max. And if it goes negative to positive, it would be a minimum. Or you could use the second derivative test, which is what I'm going to do, because the second derivative on this one is very easy to get. So the second derivative would be 6x minus 6. Plug in the values into the second derivative. So the second derivative at 3 is positive, so that tells me the graph is concave up, but the first derivative was 0, which tells me it's that point right down there. So we have a minimum at x equals 3, and to get the y value, you would plug 3 back into the original equation. Do the same thing with x equals 1. The second derivative at, I'm sorry, -1. At -1 is -12, which tells us the graph is concave up, or I'm sorry, down. And we have that point right there because the first derivative was 0. So we have a relative maximum at x equals -1. And you can get the y value by plugging in. Points of inflection occur when the second derivative changes sign. So to find where the second derivative changes sign, we're going to take the second derivative, set that equal to 0, and set up intervals around those values. In this case, we only have one value. Make sure you label your table. We are checking to see, does the second derivative change sign at x equals 1? So if I plug in 0, I get negative. So the graph is concave down from -infinity until 1. If I plug in 2, I get positive. So I do have a point of inflection. It changed concavity at an x value of 1, and then you can get the y value. -9, I think. Example 2 here. Example 2 is an optimization problem. Optimization. We are trying to find the minimum or maximum of something in terms of a story problem. So in this case, it says that we've got a box-cased aquarium with a square bottom and an open top. So I have this aquarium. My drawing skills are very good. Square bottom. These two sides need to be the same. Height does not have to be the same. And we are trying to use the least amount of glass possible. So this side right here, so the amount of glass, I'm just going to call that capital A for amount, or surface area. So the amount of glass would be equal to, I'd have to put glass on this side, which is x times y. This side here is also x times y, as is this side over here and this back side. I have 4 xy's. The bottom has an area of x times x. And I only have one of those because it says I have an open top. There's no glass on top of this aquarium. So the total amount of glass that I'm going to need is equal to 4xy plus x squared. To find a minimum, I need to take the derivative and set it equal to 0, but I can't do that because I have my area in terms of both x and y, or I could do it. It's just going to be way harder because I'm going to have two variables over here. So we want another relationship between x and y, which is the fact that this aquarium needs to hold 500 cubic feet of water. So the volume, x times y, needs to be equal to 500. Solve this equation for one variable. Y is going to be the easiest. And substitute that into our area equation. If I multiply here, I get area equals 2,000 x divided by x squared. I want to take the derivative of that, so I'm going to rewrite it as 2,000x to the negative first. Take the derivative, set the derivative equal to 0. I'm going to add this to this side. Multiply by x squared. Divide by 2. And cube root, and we get x equals 10. We should probably take a look and prove that that is a maximum value. I'm going to use the first derivative test, although the second derivative test works really well as well. My x values can't be any less than 0, so I'm going to start at 0 and go up to 10. 10 to infinity. If I plug in 1, remember this is the derivative, which I rewrote like this. If I plug in 1, I get negative 2,000 plus 2. That's pretty negative. And if I plug in 100, this is going to be 200, and this is going to be 100 squared. 2,000 divided by that's going to be really small. So this is going to be positive, which does prove we have a minimum value, which is what we're looking for. We wanted the least amount of glass. So the least amount of glass, what are we looking for? What dimensions? So we want the dimensions. So my dimensions are 10, 500 cubic feet. That's a ton of water. This is a huge aquarium. So x needs to be 10. So it's going to be 10 feet by 10 feet, 10 feet by 10 feet by y, and y would be 500 divided by 10 squared, so by 5 feet tall. Let's call this one example 3. The rest of these are kind of our old AP problems, so I want to make sure we talk through. Example 3 here asks us for the limit as x approaches infinity. So the limit as x approaches infinity is how you find a horizontal asymptote. If it's a polynomial divided by a polynomial, you can use the rules. This one is not. So instead, you want to use the Hopital's rule. Plug in infinity. Infinity cubed is really big. And e to the infinity is really big. Infinity over infinity is indeterminate form. So we use L'Hopital's rule, which means we take the derivative of the top and the derivative of the bottom. Derivative of e to an exponent is e to the exponent times the derivative of the exponent. If I plug in infinity again, I still have infinity over infinity. So we are going to use the Hopital's rule again. You could cancel these 3's if you want. Derivative of e to the 3x is e to the 3x times 3, and I already had a 3 out there, so now it's 9. We still have infinity over infinity, so we need to do it one more time. Derivative of the top is 6. Derivative of the bottom, e to the 3x times 3 times that 9. And now, whoa, now if we plug in infinity, I get 6 over infinity. 6 divided by an infinitely big number will go to 0. Example 4 here. It gives us the first derivative of a function, and it wants to know, where do we have relative maxima? Where do we have maxes? Maxes could occur when the first derivative is 0. So if I set this equal to 0, I would get x equals 0, x equals 3, and x equals -1. Because the x minus 3 is squared, we know the sign of the first derivative does not change at 3. X equals 3 is not going to be a max or a min. So we know that we could cross those two off. The problem is we can't decide between these yet. So we are going to need to use either the first derivative test or the second derivative test. I would not want to take the derivative of this. So the first derivative test is by far going to be the way to go. So negative infinity until -1, -1 to 0, 0 to 3, 3 to infinity. If I plug in -2, that's going to give me -2 times something squared, that's positive, times -1. Negative times negative is positive times positive. If I plug in -1/2, this first part is negative. Something squared is positive. -1/2 plus 1 is +1/2. Negative times positive is negative times positive. If you plug in 1, 1 would be positive, positive, positive. And notice if you plug in 4, that would be positive, positive, positive. So notice I did not get a sign change at 3. I know I have mins and maxes at 0 and -1 because they have odd exponents here. But I don't know based on that if it's mins or maxes. First derivative changes from positive to negative, that's a max. First derivative changes from negative to positive, this one's a min. We have a maximum only at -1. Let's do one more. Which one do I want? Let's do this one. This one says that we've got this differentiable function. It's differentiable and increasing for all real numbers. Question asks, on what intervals is the function g of x cubed minus 6x squared increasing? So if I want to know when is this thing increasing, I want to know when does it have a positive derivative. Increasing means positive derivative. So the first thing I need to do is get the derivative. So the derivative is going to be g prime of x cubed minus 6x squared times the derivative of the inside. So times 3x squared minus 12x. If I'm looking for where this is positive, notice g of x is increasing. If g of x is increasing, that tells me that it's first derivative is positive. So this right here is a positive number, which means I need this right here to also be a positive number. So if I factor that, I get 3x times x minus 4. And then I would start considering the answer choices here. Negative infinity to 0. So if I plug in -1, I would get -3 times -5. That's positive 15 times this positive number. So negative infinity, -1 does not work. X equals -1 does not give me a positive derivative. And then I would probably check x equals 1, because that's on this interval right here. If I plug in x equals 1, oops, I got rid of my factors. If I plug in 1, I get 3 times -3 times a positive number. Hold on. So 3 times -3, that's negative, times positive gives me negative. I'm looking for a positive derivative. Positive derivative does not happen at x equals 1. I messed up at -1 though, sorry. At x equals -1, let's try that again. X equals -1. So if x equals -1, this is -3 times -5. Negative times negative, positive times positive is positive. I want it to be positive. So -1 needs to be included. So if -1 needs to be included, it cannot be here, it cannot be here, it cannot be here. It could be that one, or it could be this one. And then we checked 1. At x equals 1, we got a negative derivative. I wanted it to be positive. So A is correct. Sorry about that. That should do it for chapter 3. I will see you guys after a bit.